So I'm sort of torn on it, making this a required lesson with a homework assignment. So I do want to touch base on there is a trig form of a complex number. I'll just put a number. Because we're familiar that a complex number can be written in the form a plus bi. You can actually rewrite any complex number as a trig equation, which probably seems really, really weird. But let me just kind of give you a quick synopsis and why I want you to know that. Is we have what's called a complex plane where you have the real part is along the x-axis, and then there's this imaginary part along the y-axis. So for instance, if I wanted, let me just give you an example, like 3 plus 4i, you would go right 3 for the real part and then up 4 up here. And then we typically draw a vector to explain that. We have this angle right here, theta. So the reason why I'm bringing that to your attention is because we can also draw the unit circle on this complex plane. And it actually makes math a little bit easier. And the reason why I say that is, on the complex plane, going right 1, so the complex number would be just right 1. Going straight up would be up 1i. And it actually makes understanding the imaginary numbers a little bit easier, because over here is negative 1. So we would just go left 1 on the x-axis, so left makes it negative, and then down 1 makes it negative I. It actually kind of explains why, when we go through the concept of I squared is equal to negative 1, because it's 2 turns, 2 90-degree turns, I guess I can explain it that way. But usually we don't explain it with degrees, we explain it with radians. So I represents 1 pi over 2 turns, and then I squared is equal to negative 1 is 2 of those pi over 2 turns, and then I cubed gets us to negative I, and then I to the 4th gets us back to 1. And so if you've seen that before, that helps explain that, but if you haven't, that's not what I want you to learn today. What I'm trying to get you to understand is there's a formula out there. It's called, it's Euler's formula, if anybody's curious. It's e to the I theta is equal to cosine of theta plus I sine of theta. And the understanding this formula gets us into calculus and even beyond calculus. So I'm definitely not going to explain this formula, but this actually helps us understand some of the rules for trigonometry with a sine of 2 theta and things like that. So just to give you an example, like if I asked you to figure out, so here's just a kind of a very lame example. If I asked you to solve for e to the I times pi, I the imaginary number, what it's saying is it's equal to cosine of pi plus I sine of pi. Well, if you think about the unit circle then, it was a terrible unit circle, but pi is over here at the ordered pair, negative 1, 0. If I scroll down a little bit, you'll get to the final answer. So e to the I pi, well, cosine of pi is equal to negative 1. Sine of pi is equal to 0. 0 times I is still 0. So in other words, that was a waste of time to write out 0 times I. So e to the I pi, this is Euler's formula, by the way, is equal to negative 1. So anyway, let's examine this a little bit closer, this thing right here. And the reason why I'm asking you to examine that a little bit closer is because if I gave you 2 different angles, we'll call them alpha and beta, all right? And I wanted you to investigate what alpha plus beta are for a formula. So as a reminder, I thought it would let me write it, but apparently not. We have e to the I alpha is equal to cosine of alpha plus I sine of alpha. And while I'm at it, I could also say e to the I beta by Euler's formula is cosine of beta plus I sine of beta. So if I asked you to figure out what e to the I of adding the two angles together would be, well, first of all, let's do some, I guess, some arithmetic here of understanding that you can distribute I into that. Okay, this is from our law of exponents, that you could rewrite that problem as e to the I alpha times e to the I beta. If this is new for you, just think about if we were multiplying with the same base, we could add the exponents. So all of these things I just wrote down are equal. So the whole premise of that is now I can go up to these equations and I can replace e to the I alpha with cosine of alpha plus I sine of alpha. That's replacing this piece. And then I can replace the other piece with cosine of beta plus I sine of beta. And now I can FOIL that. And when I FOIL, I get cosine of alpha, cosine of beta, and then plus cosine of alpha, I, cosine of alpha, sine of beta. And then the inside term would be another I sine of alpha, cosine of beta. And then the last term would be plus I squared sine alpha sine beta. Now I'm going to clean this up because that's kind of messy. The first thing I'm going to do is identify that I squared is equal to -1. And I want my part that does not have an imaginary thing in front. So cosine of alpha, cosine of beta does not have an imaginary part. I'm going to move this to the left and makes it negative because of the I squared. Sine of alpha, sine beta. And then the other piece, I'm going to factor out an I, and I have cosine alpha, sine beta, plus sine alpha, cosine beta. And you might be sitting there and saying, what in the world are you doing? Well, this piece up here is the same thing as saying that we have cosine of alpha plus beta plus I sine of alpha plus beta. So what I'm trying to show you is we're at the real part has to equal the real part over here. And what I just showed you is the sum of angles formula and why it works. And we needed Euler's formula in order to understand that. And in the same manner, the imaginary part must be equal to the imaginary part over here. And we just explained the double angle the sum of angles formula for sine. So sine of alpha plus beta is equal to cosine of alpha, sine of beta plus sine of alpha, cosine of beta. I think they actually switch those around, but addition's commutative and multiplication's commutative. So similar work could be done for the double angle formula. I'm not going to go through that work. If I really wanted to, I could assign it as homework and make you watch this video. Otherwise, I just wanted to kind of touch base that this is not magic. These formulas were derived, and you are capable of understanding. It's just we just need one formula and a little bit of I guess work to get there. Yeah, I'm going to leave it at that. And if you watch this video, awesome. Proud of you. If not, well, then you wouldn't have gotten to this point.